The following program is brought to you by Caltech.
Hi, I'm Peter Groom, class of 75, and it's my great privilege today to introduce our next speaker, Maria Spyropoulou, who is going to talk to us about the Large Hadron Collider and the discovery of the Higgs. I remember, I think it was July 4th of last year, I stayed up in the middle of the night to watch this, and there were two presenters, and she was one of them. Her resume, as I just glanced at it, I wouldn't even have time to read all the headings on it in the amount of time that I'm allotted. But at any rate, let's have a warm welcome for Dr. Spyropoulou.
Thank you. So, yeah. I'm going to be fast with this. This is liquid nitrogen. I'm going to be careful also. This is not for visual effects, okay? I got a piece of gadolinium. Okay, it's a metal, but it doesn't stick on a magnet. You see, it falls, right? So I'm going to immerse it in the liquid nitrogen here. And we're going to see what happens while I'm giving the lecture. For the rest of the lecture, that is an effect. It's not only the rock stars you get to have that, I guess. I'm going to be talking to you about the Higgs and where it's taking us, hence the Higgs Quo Vadis. This is Mr. Higgs in a recent picture. Before I start, I want to make an impression on everyone that the standard model, what we call the standard model, okay, we're going to get to that. The standard model of particles and their interactions, known as the standard model of particle physics, is the only actually predictive theory or model that can explain phenomena that span an enormous amount of orders, an enormous set of orders of magnitudes, down to the 10 to the minus 24, from the atomic scale to the subatomic nuclear to the particle scale. We don't have in physics or in any other science any such model. So the Higgs was the last grail, which by the end of this lecture, I want to convince you that it is the beginning of a big adventure in terms of understanding our physical world. So this is the outline. I'm going to describe a little bit what happened last July. And then I'm going, instead of giving you the story about the Higgs with molasses and fish in the water and fogs, I'm going to discuss the Higgs as it happened historically and how people got this idea about the Higgs mechanism. And that was condensed matter in vacuum, taking ideas of condensed matter and applying them in the vacuum. That was the demonstration we just saw. What you just saw was the reverse of spontaneous symmetry breaking, the reverse Higgs mechanism, and we will get to that. I will ask the question if it is the Higgs and how we are going to address this question experimentally. And I will talk a little bit about supersymmetry, which I personally have been looking for my entire life, 20 years, starting from the Tevatron. Aut vincere aut mori means or you conquer or you die. And at the moment, in the news, blogs, etc., supersymmetry is presented as dead, but it isn't. So the rumors of the death of supersymmetry is greatly exaggerated. Dark matter and the connection with dark matter, we do know that dark matter exists. So vincere, conquers, it's a big part of our universe. What it is, other than its gravitational interactions, we don't know. We have clues and ideas, and we describe it as if we know what it is. Also, in the context of particle physics, we say it's a new particle. We don't know that this is the case. It's a good idea, and we are well guided by the theories, but we don't know if this is if this is what it's turned out to be. For the Higgs, I will finish by commenting what are the roads ahead, where are we going with the Higgs, which new vistas it opens, and why. Let me go to a little bit to describe the landscape here. This is the French-Swiss border, and the Large Hadron Collider is 100 meters on this circle, 27 kilometers circumference. We've got two multi-purpose detectors called CMS, the compact muon solenoid, and Atlas. This is a toroidal large apparatus and compact muon solenoid. And then we've got dedicated experiments for other studies. Caltech has been working at the CMS since the beginning of the experiment. And actually, it's on the French side, CMS is on the French side, and Atlas on the Swiss side. CERN is here, the airport is here. The Large Hadron Collider is built 100 meters down with a little bit of tilt. One of the reasons of the tilt is so that we don't shoot particles to the passengers in the airport. At CMS on the French side, this is up to where the Roman Empire arrived and exchanges of currency were happening. We found Roman scissors, coins in the excavation when we built the cavern. That was a new cavern that we built at that point. And actually, the whole geological and the whole topological structure was such that there were roads and it was all lined up, and it's an interesting area there. I'm showing you here, I'm very proud of our team. Over the years, we're missing some people, but not all. This is myself and Professor Newman, and the guy in the middle is called Lynn Evans. He commissioned the LHC, and he blew it. He brought first collisions in September 2008, and we had the accident. And he had to do that. The reason why he had to do that is because such a machine, unless you have a full simulation of the integrated pieces, then your prototype is the machine that you're bringing up at the time of commissioning, and more often than not, you will have a problem with it, and that's what happened in the beginning. He's now an official of the British Empire. He got many awards. I think he will be knighted post the Higgs discovery. And actually, he's one of the people that I heard a quote from Margaret Thatcher. He quoted Margaret Thatcher saying that unless you do off-piste research, that it is not driven R&D for some particular purpose, it's very hard to have big leaps in economy and in technology. And what we are doing is exactly that. There was no good way of saying that better. I was surprised that Margaret Thatcher said it, but indeed, if you think about it, and you go back in the ages, if you just did the directed R&D, you would never go from the chariots to rocket moons. You would continue having very, very, very good chariots. These are the people of Caltech, the students, the graduate students, the fellows, the Caltech fellows, and here on the last row, I even have some of the undergraduate students. You got a pamphlet, I hope, as you were entering. These are the last year's undergraduate students doing research at the Higgs discovery on many fronts at the Higgs discovery and the searches for dark matter. Our undergraduates in the whole collaboration are recognized as, sometimes people are surprised, they ask, are these undergraduates? They're doing tremendous work and they're extremely motivated. This is the tunnel of the LHC. These are the blue part is enclosing the superconducting magnets. The superconducting magnets, if you think about it, we have one enclosure, one magnetic field, but we have two beams of same sign particles, namely protons, traveling opposite directions in the same magnetic field. To prepare this magnetic field and to design this magnet was a completely non-trivial adventure. And in fact, it was done in 1972 in Brookhaven by John Blewett, who was a magnet physicist. He tried to convince the people of Brookhaven that we could do a machine called Isabel at the time, a collider called Isabel, but this didn't go forward. People afterwards tried to convince the SSE management that we could have one tunnel instead of two, but this didn't go forward. However, the LHC people, the Europeans, went gung-ho on this dual-core magnet design of the LHC, which turned out to be the key in order to be able to fit in one tunnel, in one pipe, both beams of protons and collide them. So this was completely non-trivial achievement. And I should say, here's another shot of that. This is open here. These are the interconnects here and here of the superconducting filament. The cables. The strands of the cables, there are niobium, titanium. The filaments are about 10 astronomical units, with a little bit left to go to the moon and how big they are. And they are soldered from this supermagnet on that side to this dipole magnet. And the reason why we had the explosion is because these cables carry about 12,000 amps. And they are soldered, and on top of them, you've got what we call the bus, the copper bus. In case they get quenched, the 12,000 amps go in a dump resistor. So in our case, if you don't have them completely connected, you will have an arc and an explosion. That's what happened. And now the superconducting magnets, in order to be operating, they need to be at very low temperature, close to 2 Kelvin. And this is the feed of the helium that keeps them at this temperature. When the explosion happened, there were no particles, so there was no radiation. But the helium, which is fed in here and around the magnet, was brought to room temperature from liquid. And so it expanded, the volume expands by 1,000. And the forces that were exerted on the physical forces, you would have helium collisions, basically. And the physical forces of when they found a barrier somewhere in the tunnel knocked down 53 magnets. That was in the fall of 2008. We recovered very quickly. We fixed all the magnets. And we started the physics program towards the end of 2009. In fact, I was running the experiment when we took the first high-energy collisions and we beat the Tevatron, my previous collider, and the experiment that was there. This is the impression, a little short clip from 2005. This is of historical value of the LHC tunnel. And you see, as we're going through, we will see the feeds for all the electric and all the dump resistors and the cryo. It is said that the LHC, there is no such an experimental adventure of this scale and this complexity that was ever done by humans. Just to show you what happened, this is not at the point of the explosion. The matter annihilated, there was nothing left, it was dust and soot. But at the point where the barrier kicked the last magnet, this is what happened to the magnets. And this is the situation we were left to fix. So, well, this is our experiment, the experiment that Caltech is involved and our students. It is, as a Lego design, it is made of 12 modular pieces. It looks like, from the outside, it looks like a cylinder, and it has many sub-detectors as you go closer and closer to the beam, and it has 2 lids. This part, the part in the middle, is called the central part or the barrel, and the parts closer to the horizon on that side, they're called the end caps and the forward regions. What we see here is the central part, the barrel, and we see another piece of ingenious design. This is our solenoidal magnet. It's also superconducting. It's at 3.8 Tesla. The magnets of the LHC, if you do the calculation, in order for the particles to go at the speed of light and be kept at 27 kilometers, they have to have 8.3 Tesla. This is 3.8 or 4 Tesla. And it is impressive because you do have this in medical applications, but you never had such a magnet that has such a big diameter. So if you calculate the energy, you can put a hammer in there. This is 6 meters. So if you calculate the energy, it holds 2.7 gigajoules. This is a humongous amount of energy. When we integrated it, and for the first time, we powered up this magnet, we were not sure if it's not going to throw part of the detector to Lake Geneva. It would have this power. So in prototyping it, it's a smaller scale and smaller complexity than the entire LHC. So we were confident that we did have all the simulations and we were not running this risk, but it's a prototype still, okay? The one that exists, it was a prototype. So now, one thing about the data, you hear it a lot, but big data, and what we talk about big data right now, is something that happened in high-energy physics and collider physics specifically since a long time. At the LHC, we've got 100 million channels per detector, approximately, and the collisions are happening nominally at 25 nanoseconds. So that gives you, depending on the event size, and that's a matter of computing and software architecture, about 1 petabyte per second. Now, you can compare this to the global World Wide Web traffic, which is 5 terabytes per second, or you can compare it in 2010 to the entire load of Google, and these numbers are from 2011. So we are really subject to tremendous amount of data. We keep an enormous amount of data, which immediately, there's not a single computing site in the entire universe that can hold all this data. So immediately they get distributed, and Caltech actually is the place where all the innovations that for the grid to happen and distribute the data, as well as more intelligent grids that are processing the data as they're being moved out. This is the place where all this happened. Actually, before my time, Professor Newman was one of the biggest inventors of this. This is from the Department of Defense, how they describe the data and the distribution of data before and after the LHC. This was before the LHC, and this is after the LHC. With all this data of the first 2 years of running, we got the discovery. So this was July 14. The discovery was captured. Well, the discovery did not happen on July 4th, of course. We knew that we had signals since we opened the blind analysis, and we saw them starting in May and June. And then we had many tests before we did the announcement. You see here our director of CERN. Some of our students and postdocs were out waiting to be there, and this was in Australia, in Melbourne, where the biggest conference was taking place. And this is Mr. Higgs, who was crying, and he said to my friend Fabiola here, "I never expected this to happen in my lifetime." Subsequently to that, he said, when he was asked by the journalist, "What is the Higgs?" he said, "I have no clue." And I will return to this and why I think he knows what he's talking about. Now, there's one thing to be said about the Higgs, or a Higgs, or the particle we found that looks like the Higgs. I think it has captured the imagination of people for many decades. I remember when I was a student traveling to Geneva 20 years ago as an undergraduate to be part of an experiment that I was sitting next to somebody who was an academic, and I was explaining what I'm going to do at CERN, and the person said to me, well, oh well, but the science will never be able to tell us where the mass is coming from. They have all these stories, but really that's not your science. What you're trying to do has a dead end, because that's not going to happen. And well, lo and behold, I don't know the person, but obviously with the motivation of finding things that people think are impossible to find, you actually get somewhere. Where we got, we're going to see. Science is a magazine that covers usually biological sciences, and we were on the front. The Economist, well, you see, The Economist thinks that we have to do something with astronomy and acrobatics. So they have gymnastics and astronomy and astronomical things. They have Economist coined with the Higgs discovery. This was the first time that the New York Times had a full section on the full science section on one topic, the Higgs boson. And this is my friend Fabiola, who was number 5, the time of the year, the Time selected person of the year, with, I think, Barack Obama was number 1. So now I'm going to describe some of the insights that we saw here at this demonstration with this piece of gadolinium, and what kind of symmetry was broken as the temperature changed that made it from ferromagnetic to paramagnetic. These were the ideas that led Nambu to describe what they're called the Nambu-Goldstone boson modes. They describe spontaneous symmetry breaking, and spontaneous we take with a grain of salt because there was a lot of action here before spontaneous symmetry breaking happened. There was temperature changes, something had to trigger that. And also, I will say this now, you know it from your freshman courses, that electromagnetism, which was perfected and united with the weak nuclear forces in this institute with Feynman and Gell-Mann, is sourced by sources which are charges and currents, okay? And the question that people naturally ask is, what is sourcing the Higgs field? I gave an example here of a symmetry breaking where, with the change of the temperature, we went from spontaneous magnetization below 20 Kelvin, below 20 degrees centigrade. The gadolinium is a ferromagnet, is fully magnetized. The little spins in the atoms are in one direction. And so, and below that and above that temperature, the little spins are in all directions, and it is paramagnetic. Something like that is the spontaneous symmetry. This idea was the exact idea that brought us to the electroweak symmetry breaking that gave us the Higgs. The Higgs is one of the Goldstone boson modes that Nambu was talking about. You see this? This is perfect rotational symmetry when this little ball is on the top of the pant. If you think about it as the bottle, this is the top of a bottle, or we usually call it the Mexican hat, and this is the rim. From going here, you have a perfect rotational symmetry. Here, the symmetry is broken, and you have an infinite state of what we call the vacuum here. That means that the vacuum and the Lagrangian do not respect the same kind of symmetry. And this is the picture we use for symmetry breaking. And these are the analogs in Nambu. I want to impress on you that the discovery of the ideas of the Higgs mechanism, spontaneous symmetry breaking, and the standard model of particle physics so far got 2 Nobel Prizes. And in October, there will be a 3rd one. for Mr. Higgs because his name is the particle that we just found, and some other people. Nambu and Goldstone, they got Nambu and from Chicago and Goldstone, actually from Chicago also, they got the Nobel Prize for the importance of spontaneous symmetry breaking and the problems of massless bosons. These are the kind of Goldstone bosons that are generated when you have the symmetry breaking. And the example I gave you here, that it is a similar example of spontaneous symmetry breaking that is happening in the Electroweak model of particles and their interactions, is the ferromagnetic one, where there is a broken symmetry. Which symmetry? The rotational invariance. It's the spins of the particles, of the atoms inside the metal that we saw. And this happens in other materials, in crystals and in superconductors. And going from this symmetry, which was just the rotational invariance, to the symmetry in the crystals that is broken, which is both translational, as you have in the crystals, you have the atoms in particular orders and steps. Both translational and rotational, therefore, when it's broken, we call these phonons. In the superconductors, when we have a new sense of more esoteric symmetry called the local gauge invariance, broken, you get something else, and you get something which looks like a massive photon in superconductors, the Cooper pairs that you have heard about. So these are the ideas that Nambu was talking about, the case of cross-fertilizations, because these ideas started from many body systems, from things that you actually can study with your hands, not quantum ideas of flying things that you only have concepts about. Anderson in 1962 took it a step farther and actually described exactly what that local gauge invariance superconductors would be. It would be something like a massive photon, and the problems in symmetry breaking of creating only massless, without mass, bosons was reconciled in some sort of a cancellation. He went on a very big, that was a leap in thinking on how he would reconcile the local gauge invariance breaking with not a massless boson, but something that was a massive, almost a massive photon. It was a set of electrons that we call Cooper pairs now. Now, there was one step more. That was 1962. One step more in 1964. What happened was that Higgs did the relativistic analog. In the relativistic analog, all the math was working the same. But now, I can't show it to you. There is not matter. There's no condensed matter. There's no material. It's the vacuum now. And this is why it's difficult to describe the Higgs mechanism without using analogies that sometimes are weird. What is happening, however, this is we've got the Goldstone bosons, and we've got 1, 2, 3 of them. These are 4 Higgses here. 3 of them are written up, and they are creating the W plus, W minus, and Z. The W plus, W minus, and Z, we found they're massive, and we found them in the 80s. So these were the first three phases, quantum phases of the Higgs boson, and that's the little one that remained. It took 40 years. We found it now. We found it in July, and lo and behold, the standard model for which Steven Weinberg, Salam, and Shelley Glashow got the Nobel Prize, was completed. This used to be a nefarious idea, and that was another huge leap, because Weinberg took all these ideas from everybody, and he said, I will make sense of everything that we know experimentally about all the subatomic particles, and that included the quarks and the leptons and the neutrinos and the forces. I will make sense of all of this together by using the Higgs mechanism. And the Higgs mechanism will be such that it will give mass to this, and to the W, plus minus the Z. It will leave the photon and the gluon massless, and it will give masses to the quarks and the leptons. The neutrinos remain massless, and this is a puzzle still in the Standard Model. You see, Shelley Glashow is not in this picture because he was my teacher, and he was calling the Higgs the toilet of the Standard Model. The reason was because he thought that it was a cop-out. It was beautiful mathematically. It was working. The analogy from condensed matter theory was working, but why would it have to be that? This was not, to him, this was appearing a very fantastical thing. And a posteriori, it is. I think I am stunned that we actually found what we predicted, what these people predicted, the theorists predicted. It's a big, big victory for human thinking and for the experiment. It's a fit. So the Higgs boson, as I showed you before, this is the equation. This is the kinematics and the equation of motion, let's say, for the particles. I don't want you to understand this at all, but I want you to keep in mind that we have the Higgs breaking the symmetry. This is the Lagrangian before breaking the symmetry, and this is the Lagrangian after breaking the symmetry. So there are all these terms, and it's a mess. But however, it's such a beautiful mess. In which sense? We got light in these equations. There it is. We got electricity and magnetism in these equations. There they are. We got the weak nuclear forces, the way the sun works with the thermonuclear interactions. We got them here. The W and the Z are the weak gauge bosons that got the mass from the Higgs. And we have mass. The Higgs handshakes with the electron, the U quark, the W's and the Z's here, and those states acquire mass. That was the scenery at the auditorium at CERN. I think I was just behind this guy there, but this is Fabiola, and this is Gianotti, the head at that moment. She was running the other experiment, the Atlas experiment, and Mr. Higgs, who was very happy because the experimentalists did actually go about this and found it. So now there's many questions we can ask. We have measured the particle that, we have discovered the particle in the decay modes of photons and Z bosons. And that looks like it has it's the right way to go about the Higgs particle. But however, we need to make measurements of its properties, detailed measurements of its properties before we say that it is really the Higgs. And these properties are determined, are being studied by the way it's produced. The Large Hadron Collider collides protons, which is a collection of quarks and gluons. And in fact, at these high energies that we collide them, it's a gluon collider. This is the biggest mode of creating the Higgs. As I will show you in a bit, it goes here from gluons, which are massless, and in a mode that decays into photons, which are massless. So this is kind of ironic, because one of the decays that we found it first, the diphoton decay, is coming from massless to massless. But there is loops here with massive quarks. This is, again, a fit for quantum field theory. This is how it decays. There are many decay modes. Don't let this get in your head too much. The main thing is that we know how it decays. We can calculate in which states it decays. And in every calculation of these famous Feynman diagrams, we got the particle shaking hands with the particles that it gives mass. So this is the Higgs particle with two bottom quarks. If we measure that very well, and we can measure the coupling of the Higgs to the bottoms, then we start getting the properties of the Higgs boson and how it couples to all masses. Similarly here, and non-masses, by the way, because here we've got the tops. These are massless, these are the photons. This is what the detector is measuring. This is a muon in CMS. It will traverse the entire detector. This is the one section that I'm showing you here transversely. Inside here, there is tracking. The muon leaves tracks, and then it's electromagnetic calorimeter, hadron calorimeter, the solenoid, and the muon chambers. That was an electron. It stops at the electromagnetic calorimeter. A neutral hadron, it doesn't have charge, so it zips through the camera, the silicon camera, and it stops in the hadron calorimeter. A charged one, it leaves a track, and it stops in the hadron calorimeter. And this is the photon. It will zip through without doing anything in the tracker, and it will stop in the electromagnetic calorimeter. This is what Caltech is involved in, the electromagnetic calorimeter, in the hadron calorimeter, and also in the trigger for all the particles and for all the Higgs. There is one of the candidate events. We think it's if we make the invariant mass of these photons, it falls in the mass of the Higgs. It's 126 GeV. It's a fantastic candidate event. And in order to get to this, I will mention here a technical detail that we have to calibrate 76,000 of crystals of lead tungstate to a % level in order to be able to measure the Higgs. And we do that at Caltech. We build the laser system that is doing the calibration of the crystals. As they get irradiated, the crystals lose transparency. And then they recover, because of the color centers annihilated, they recover the transparency. And so you have to monitor this live, and that's what we do. It runs, the laser system runs every 40 minutes. Our graduate students were on call all the time the previous 3 years that we were taking data in order to be able to make the discovery. The other golden channel is the channel that has 4 leptons. Based on this channel is how we build these detectors. We build them so that they discover 4 muons at all ranges of from 50 GeV to 1 TeV energies of these muons with 1% precision. And that was the single one specification requirement in order to do the full specification of the detectors. Here you see them 4 muons. And in the case that one Z boson decays into 2 electrons, you have 2 muons and 2 electrons. 1 pair from one Z, 1 pair from another. If I make the invariant mass of all this, it has to give me the Higgs boson, all right? And that's what it happens. Now, I want to mention that this all is happening amidst, in every collision we have, we've got actually up to 40 interactions. So there are 40 events in an event. But you see here, these are the vertices looking on the beam direction, on the Z. This is about 15 centimeters, and we've got a millimeter resolution for each of these vertices. And well, you see that these 4 muons, these 4 leptons come from one single vertex, so we know it's one event. Let me show you a little clip of, from the beginning of data taking, how the data looked like in Atlas for the diphoton channel, until we exclaimed that this little blip here is the Higgs. We wouldn't have exclaimed anything if we didn't have it in another channel, all right? So the other channel was this one, is the 4 leptons that I told you, the golden one, 2 Z bosons, each 90 GeV. I'm lying, it's a Z and a Z star, it's not on shell, it's a Z and a half, because the Higgs is 126, it's here. 4 leptons make 1 Higgs, that's it. And 4 leptons make also a Z, because we have an internal calibration in our data, which is the Z boson, decaying into 2 leptons, but also we have a radiation of a photon that also can decay to 2 leptons. However, these 4 leptons, we make a Z mass and not a Higgs mass. And the Higgs, when it decays to 2 Zs, to 4 leptons, will make a Higgs mass. Well, one of the first things we did is that we said, with this data, what can we do? And the first thing we can do is we can reject all possible evident imposters. In other words, all bad theories immediately will get rejected. And this is the type of results that say that we reject the pseudo-scalar interpretation compared to the scalar, which is the standard model Higgs. But that doesn't mean we have measured the spin of the Higgs yet. There's a lot of work. So all the evident bad theories, with this data, we have junked them. Sorry for the theorists. Still, the question is, can we have, how can we know that this is the only Higgs and not many Higgses? And this is a very good question. In fact, in supersymmetry, we've got up to 5 Higgses, and supersymmetry is an extension of the standard model that it is mathematically, you might say, even more beautiful than the Higgs mechanism, because it does everything that the standard model is doing, and it gives you the dark matter, and it gives you unification. It gives you, mathematically speaking, and in terms of physics elegance, it's really tremendous. Whether nature is doing that or not, we can't say. We have to measure it. We have to find it. So this is a statement that I want you to take of that supersymmetry predicts at least 5 kinds of Higgs bosons that are differing in their mass and other properties. And what I ask my students is a joke for that. And the joke was, well, they found 5 pictures of Higgs that differs in different times, that differs in mass, in his mass and other properties. I'm going to say for supersymmetry a couple of things, and then I'm going to close, going back on the implication. Well, supersymmetry, first of all, people, when they say that they are depressed, that supersymmetry is not found, I want to remind everybody that we have run the machine at a little over half the specified energy. And let me show you in numbers. The Higgs boson has a rate that is up there. You don't need to look at anything. Just this axis is the rate of a process, of a physics process to happen, and this is the mass of the particle involved. So the Higgs is somewhere here, 125, and it had a rate up here. There were a lot produced. Supersymmetry is down here where we're looking right now. So we need quite a lot more data and more energy before we can say that it is completely excluded. So this is a Caltech-made plot of how we express what part we excluded of SUSY, and I want to make sure that everybody understands that some SUSY models, and formally there are infinite of them, have been excluded. A colleague of mine at SLAC calculated that about 1/3 of the models of the full, what is called parametric MSSM, which is the minimal supersymmetric standard model, have been excluded. And to close now, well, I want to remind how we started. We started when I said that the electromagnetic field, and upon it was built all the Electroweak model and the standard model, the Electroweak standard model. We know what sources it. It sources charges and currents. That's freshman E&M. The Higgs field is sourcing itself, and this is a very important thing to remember. It permeates the entire universe and it sources itself. And it is a new force, essentially, that we have found that it is not lying in a gauge boson. With this, I want to tell you one last thing. It has the Higgs field is self-sourcing, and it has a self-interaction strength lambda. And also, it has quantum corrections. Now, let's focus 1 minute on the lambda, because that was recently in the news and people got scared. If this lambda, now we have the numbers so we can calculate things, but if this lambda goes negative, then this hat, this rim here of the Higgs hat turns around, okay? This is how it looks like. I had a postdoc made a graph here. Oh. This is the Higgs potential. This was the vacuum. We were here. And as we turn lambda, as the lambda is negative, and we look at the strength, well, there is another vacuum. This is what was in the news recently. The fireballs of doom of the universe. What is going to happen? And I want to mention that this possibility was actually studied for the first time in 1979 by Politzer and Wolfram here at Caltech. And now that we have the numbers, we can say whether this is the case or not. In fact, if you believe in supersymmetry, this is just the fact that the universe is in the brim of doom in 10 to the 100 years, if I want to be truthful, then it's just a coincidence. But what it is telling us is that there is something more other than the Higgs. How the Higgs is, how spontaneous electroweak symmetry breaking is happening and mass is created at the beginning of the universe in the electroweak phase transition cannot be explained with the Higgs only. So there are many options. People are talking about Planck scale boundary conditions. There is perhaps, as we have spontaneous symmetry breaking, there are more symmetry breakings that are causing the spontaneous symmetry breaking of the electroweak sector, or perhaps the Higgs is a direct portal to dark matter. This is a nice, simple model that connects the Higgs to the dark matter, and this is where physics and astronomy, this is really 2 streets in Rome, in the University of Rome, in Sapienza. Physics and astronomy meet together, and here, is Zwicky, 70 years ago, here at Caltech, he talked about the dark matter based on the virial theorem only on gravitational interactions. So in the case we're talking about now, the dark matter can have interactions through the Higgs. If this is the case, then we have a chance with the direct dark matter experiments to find dark matter. Last time when I was here at the alumni 3 years ago, it was after the big explosion, and I said to people that with optimism, I can promise you a Higgs. Now, I cannot promise you a dark matter in the next 3 years, but if we find it, I will not be surprised. With this, I want to close with a final thought, which is this. The meaning of the Higgs discovery is that we really have to think different. And I think what Mr. Higgs was saying when he said, I have no clue, is this. Because where this is taking us, given what we have observed and what we have not observed, it means that we need to think different in order to go a step to the dark matter and the dark energy of the universe. And I think paradigm shifts are awaiting for us and discoveries. Thank you. 2 minutes.
Thank you very much, Dr. Sporopoulou. Do we have any questions from the audience?
Thank you very much. Wonderful talk. I want to ask you a question about your intuition in science, not your facts as an experimentalist.
Yes.
When you look at this beautiful mess of the standard model,
Yes.
is it correct? Is the universe really that complicated?
The question is, when you look at this
Mess of the, yes, you are talking, we have a nice mathematical mess, indeed. It's this one. You remember it. It was looking intimidating for anyone, including all of us who have had to go through this in quantum field theory at school. This one. Right. Well, so I will speak to you with my knowledge. So my intuition will come a step forward with the knowledge that we have and I have so far. This is a language that it works for nature so far. This is not, by no means, it says that it is describing nature fully at all, and all phenomena at all energy scales. It happens to describe nature up to the 10 to the minus 24, up to the level that we have understood, that we have probed, if you want, space-time. When we talk about the Planck scale, this is where you're challenging me. I can safely tell you that we don't know what we're talking about. As an experimentalist, and I think all my experimental colleagues will agree with me, because we don't have experiments that go to the Planck scale. The theorists do. Their intuitions say that we have Gedanken experiments that go to the Planck scale. And for them, a black hole is a laboratory. It's a thinking laboratory. The physics of gravity, for example, and how you connect it with a black hole, and the physics that I described to you. If you want to talk about mess, that is a big, big mess. If you ask them, they will tell you, we have string theory, it's elegant, it's beautiful. If you look at it, it's a language, it's a framework. For them it works, but without experiment, I cannot say anything. This language, for me it works because I have all the experimental measurements up to that level that work. The intuition now of whether there's going to be more than one Higgs and how we will connect with the rest of the questions, that is a huge number of questions regarding, even now with the Higgs, why do we have 3 families? What did we need the muon and the tau? How baryogenesis happened really? I say it's self-sourcing, but why is it self-sourcing at 10 to the minus 11 second? Is the Big Bang correct? What, all of these intuitively, I think my intuition is that we have to change the way we think. But this will never be violated. It will be embraced, but it will never be violated. For this, I am sure.
Well, last question.
I'm concerned about the cost due to this
Are you an American citizen? Sorry? You're a taxpayer. I'm very glad for that. So, me too. First of all, the Higgs discovery and the claim of the US on the Higgs discovery, which without the US it wouldn't have happened. However, for us, it happened very cheaply because we didn't build the SSE. We saved a bunch of money. Now, for the scale of the cost of this type of experiments in the future, I can promise you that unless we figure out some innovative technology on how to do, I don't know what, plasma acceleration, wake field acceleration, beam me up Scotty things, I don't know what it's going to be, but otherwise we look dumb even because we can't just scale up and go to the Fermi dream around the world. No, we have to do something smarter. We still have not reached that, and the yield, the physics yield of the discovery is so big that all the intermediate technologies that we have developed have paid the LHC already, what we have done. So far, as we are now, and maybe one more generation, we're not going to discuss the cost versus benefit. Somebody made actually a real study, and we come way ahead on the cost benefit for economy, for the society, for technology. You cannot promise, of course, these things ahead of time. So, and also you cannot make a case in the politicians in Washington that we want to do this because of a spin-off. That's a bad business plan, and we don't do that. What I started with saying is that off-piste, not direct R&D driven for something in particular research has proven to make huge leaps. And this is a framework for thinking different. This is building a framework for thinking different. So for the moment, I think we're okay, but what you are saying is very valid, and for the future, where we are going with this, we're not going to be the Planck collider with this kind of technologies and ask you to pay for it. No.
One thing I might mention is that in the future, when this thing is upgraded, we're talking about going up to what,
33 TeV, but we don't know the technology of the magnets yet because it's supposed to go in the same tunnel. And I should say that when we started the design of this machine, the magnets, the dipole magnets were not proven to work. They were prototypes. So we, in Europe at that time, historically, this is an interesting story, Europe at that time wanted to use science in order to get out of the mess of the war and to start bringing together Italians and Germans and Greeks, etc. That was a mess. And in order to do that, that's why also it's in Europe and in Switzerland, they said they were going to do it through science. And they said, one of the targets they said, I hope I'm not recorded or some of this has to go out, was that they had to beat the US. It took them 50 years, and the cancellation of the SSE and some hiccups that we had here, mostly I think political or bad management or post-military, post-war kind of glitches, unavoidable in a sense. But then they caught up. Without what we have done at Stanford, at Berkeley, at Brookhaven, especially at Fermilab with the Tevatron Collider, and with all the intellectual, yes, we wouldn't have done
One thing I'd mentioned, you were at the Fermilab. That was the predecessor to this.
Yes.
And at that time, the highest energy accessible by the lab was what?
2 TeV, and we jumped to 7 TeV, and with 7 and 8 TeV 2 runs, which was half of the 14 TeV of the LHC, we had this big discovery.
And the promise of this is to go up to 30.
33 TeV in 2025.
So you're looking at 15 times greater energy. Who knows what's going to be there?
We hope a lot.
That's what makes it exciting.
Yes.
Thank you, Doctor.
Thank you.